Hi, welcome to Unit 51. Unit 51 is really our starting point for studying stars because the sun is the closest star to us. So we're going to start with it because it's going to give us a stepping, basically, if you wish, a door to the rest of the stars so that we can have more discussion later on. Okay. So here we're going to describe the main features of the sun and its structure, basically. Explain what keeps it together, because we say the sun has a lot of gravity, and it does. So why wouldn't it collapse further on itself? Okay, well, it has a lot of temperature, and these two they come to a certain balance. Okay, and that's what we're going to explore, and then we're going to explain the magnetic field and basically the outer atmosphere of the sun. Okay, so this is how the sun looks like. It produces a lot of energy, 10 to the power 26 watts. That's 10 to the power 26 joules every second. So if you were to gather a lot of materials, wood for example, and try to burn it to produce that much energy, you wouldn't have enough wood in the entire solar system put together, including the sun, time and time over, just to provide the enough energy to be burned that many billions of years. So that's not really what causes the sun to produce that energy. If you were to consider, for example, the relic energy from when the solar system came together, do the conversion basically of gravitational potential energy, the force of gravity, the potential energy of that into heat. Because as things get closer and closer, more and more collisions basically start to happen, and heat increases because of it has to do with how fast objects are moving. So you take that much amount of heat and you say, okay, I'm going to let it cool on its own. How long that will take? That is not going to be enough again to produce that much energy every second. So there must be another source of energy. That's why people were confused before the turn of the 20th, the 19th century, basically going to the 20th century in the 1900s. What source of energy produce is really necessary to keep the sun going for this many billions of years? And we know that it has to be that old because of other studies related to the geology, for example, of the earth and also the meteorites. So it was a puzzle until nuclear energy later on was basically discovered, and then from there we know that inside the core of the sun there must be some nuclear reactions to provide that much energy. 10 to the power 26 watts. That's joules every second, far more than what we produce here on Earth for many years over. Okay, so it's really a lot of energy. Okay, and it's the source of energy that we have on Earth anyway. So if you're thinking carbon-based energy, like hydrocarbons, for example, they got their energy to begin with from the sun. Okay, so this is how the surface of the sun looks like. Okay, the part of the sun, of course, we have the atmosphere of the sun. The part that we see from the sun is the photosphere. Okay, this is the surface we can see. That's the light that basically reflects from that surface. If you look inside of it up close, you're going to see this formations in here, this bubbles in here of the granules. That's basically how the surface of the sun looks like with an up close form. It's really a huge amount of gas, mainly hydrogen and helium. That's what the sun is. It's gas. It is. So if you're wondering, okay, well, how much other metals are? Well, it's practically nothing. Look at the density of the sun. On average, it's 1.4 kilogram per liter. That's what the air is. Okay, so it's really air, but not even this air that we have, which is mainly nitrogen and oxygen. That's a heavy air that we have in here. It's actually a lot lighter than that. The two lightest elements in the periodic table. So the distance is 150 million kilometers. That's one astronomical unit. The radius is about 700,000 kilometers, which puts it at about 100 times wider than the Earth is wide. And inside the core, inside the sun, the density is higher. It's about 160 kilograms per liter. That's a lot. That's actually, the Earth has about 5.5 kilograms per cubic meter. So it's a lot less than that if you convert it to liters, because there are 1,000 liters in a cubic meter. So you do the math, okay? Its surface temperature. The temperature on the surface is about 5,800 Kelvin. Okay, we had a unit before, and please go ahead and review it, that connects the temperature to the wavelength. 5,800 Kelvin, if you use Wien's law, it corresponds to about 500 nanometers, which is the green light. Okay, that's the middle of the spectrum. That's why the sun appears white. Its central temperature inside the core, though, can be as high as 15 million Kelvin. You need that temperature, and not too high, by the way. If it's higher, then helium will start to fuse. So that's the temperature that is necessary for hydrogen to fuse, okay? So that's the temperature inside the core of the sun. Again, there are some units in here referring these points. Its composition is mainly hydrogen, as I said, and helium. And the rest 2% is other elements, including carbon and oxygen and iron and other elements, okay? This is what I was talking about, 10 to the power 26. I mean, when you're talking 10 to the power 26, which 4 times that much, okay? That's the amount of energy produced every second. Again, we saw another law that justifies this expression. It's called Stefan Boltzmann law, and that gives me how the temperature to the power 4 is related to the amount of energy emitted by an object. That's basically how we can also relate this frequency this way. This temperature, 5,800 Kelvin, to the surface of the temperature to the amount of energy that is emitted by the sun. It's easy. All you have to do is take swimming pool, for example, let it be exposed to the sun, measure its core temperature of the swimming pool, not just the surface, okay? And see how much it rises in, let's say, 1 hour, 2 hours, okay? 4 hours. And if it goes by 1 degree, there is actually stuff that you can learn, that if you heat 1 kilogram of water by 1 degree, you need about 4,000 joules. That's how much we know. Since we know how much energy is hitting the surface of the pool, then we can extrapolate it to the entire 4 pi times this distance squared, because that's the entire energy that is dissipated on the entire sphere away from the sun, one astronomical unit distance away from the sun. So that's basically how the math justifies these numbers. But forget about the math. Appreciate just how big these numbers are. But I'm telling you that there are solid foundations for where we're getting all of these numbers in here, okay? The surface of the sun is just the outer surface in here, which is the photosphere. As I said before, the radius is about 700,000 kilometers, which is about 100 Earths that you line them one next to one another to reach this distance. Of course, 100 Earths times 100 Earths times the other depth, 100 Earths, that puts it 100 times 100 times 100. That's 1,000,000 Earths will fit inside the sun. 1,000,000 Earths will fit inside the sun, because in each axis there is 100. 100 times 100 times 100, that's basically million Earths, okay? Again, you have the photosphere, which is the outer layer. The corona, which is way outside, and that's made up of super fast moving particles. Its temperature is higher, but the density is so low that we don't see that. We see it only during probably a solar eclipse. And then we have the chromosphere, which is the atmosphere of the sun. And then the photosphere, that's the one I was talking about earlier, but that has those granules on its surface. And then you have these formations in here, which are due to the magnetic, activity on the sun. And that's the outer layer. Then when we go in, we have the convection layer. Remember the convection layer about the Earth? Also, it was in one of the other units. That's similar. So basically, it's like a bubbling, if we wish, for example, when you're cooking something. The inner part is super hot. The outer part is a lot colder. I mean, 5800 Kelvin is not that cold, but it's cold compared to this temperature in here. So now bubbles, the gas starts to basically move around and transfer with it the heat as it moves from low temperature back, heats up, and then to carry that heat with it. And that's how the sun is getting rid of that excess heat. Okay. There is a radiation zone in here. This process is not going to happen because it's moving super fast. And that's the radiation zone, and that takes between the core and the convective zone. And the core itself is where all the action is happening. That's where the energy is produced. That's the one that has 15 million Kelvin. So you go from 15 million Kelvin down to about 5800 Kelvin. That's basically how the sun is. Okay. Again, the photosphere is visible. That's the one that is about 500 kilometers thick, and its surface temperature is about 5800 Kelvin. I mean 5780 Kelvin if you really want to be specific about it, okay? The entire sun is ionized gas because those temperatures, hydrogen cannot keep its electrons. Helium cannot keep its electrons. So it's really a mix of floating electrons everywhere, with ions that are mainly hydrogen, protons that is, and helium. That's what the sun is. 98% of its constitution. The rest, 22%, are just the other elements, okay, that you can see them. The sun, as I mentioned before, is really a balance between the two. Gravity tends to pull everything in. Heat tends to push things away, okay? And the balance between the pressure coming from the heat, the high temperatures, and the gravity, that's what keeps the sun from further collapse. Okay? That's actually what regulates also the sun. Because if the core gets too hot, hotter than usual, the sun expands. And as it expands, the temperature starts to cool down. So now it goes back to its normal temperature. But if the core gets too cold, the gravity will start to win now. It start to compress more and more, causing the temperature to increase. And hence you have a balance, at least for the most part of the life of the sun. While it's fusing hydrogen inside its core, the sun is sitting in its own size. It's neither increasing. If it does, then in this case, the temperature inside starts to decrease, which causes the sun to collapse. But if it's a collapse, the temperature increases, and the pressure from the temperature pushes the sun away. So it keeps it in its form as long as it's fusing hydrogen. At some point, it's going to run out of hydrogen inside the core to fuse. So at that point, gravity starts to win because there is no more nuclear reactions, or at least the rate starts to decrease. Then in that case, starts to compress. And if it compresses, the temperature starts to increase inside. And as it does, at some point, it triggers the helium to fuse, and that will bring it to a new phase of its life. Okay, at this point, it's not there; it's just in the fusing hydrogen in its core. We're going to talk about that in another unit. Okay, so what is that thing coming from the pressure? If you take any gas, okay, a certain amount of gas, okay. This is if you took any chemistry or elementary thermodynamics and physics, you know about it. The pressure, the volume, and the temperature are related for any gas, okay? And the expression for it is PV equal to nRT. In general, you can divide by the volume and you express it in terms of the density. This is how physicists tend to express it. The pressure is a constant, just that has to do with the ideal gas, basically. If it's an ideal gas, if it's not that constant, it's slightly different. Pressure is proportional to the temperature. That's the main thing, and the density. Okay, that's basically what. You increase the density, you increase the pressure. If you keep the temperature the same. If you keep the density the same and you increase the temperature, the pressure increases. So that's basically what you play with these three numbers. Okay, forget about this constant. That's a number that doesn't change. It doesn't matter what the gas is. That's the same number. So that's the law that governs basically the process. I'm going to try to blow on a balloon. Okay, you increase the pressure on it. So in this case, the volume starts to increase. Okay, to maintain that stability. And if you keep the room from further increasing, then the pressure starts to increase. In this case, the temperature has to keep up with the pressure. Okay? The sun also experiences sunquakes, similar to earthquakes, okay? And because the sun, although it's not a solid object, but it experiences all kinds of activity, and based on that, we deduce a lot of its composition and things like that, okay? By the way, a lot of the studies are based on models, computer models that are confirmed later on by observations, okay? Numerical simulations with observations. Again, I mentioned the fact that the sun is many layers. The main thing is actually the core. That's where the energy is produced due to nuclear reactions. Because the wavelength that emerges from it, and we'll see it in another unit, is super short wavelength, extreme high energy, extreme high frequency. And the density is so high. There are a lot of electrons in the core of the sun, mainly electrons. So telling me, how about the ions? Yes, there are ions, but as far as this wavelength, they really are not going to be affected by the ions because the ions will not absorb a lot of their energy. They really require electrons. So that photon that's produced from the nuclear reaction hits an electron. Part of its energy is taken by the electron throughout the system, the whole core. That's what maintains the temperature of the core high. And now that photon loses some of its energy. Not much, but just enough. Then it keeps on colliding. How long this process takes? Hundreds of thousands of years. So the photon that just hit my eye right now from the sun was not produced today or yesterday or a month ago or 10 years ago. More than 100,000 years ago since it was produced. It took it that long to escape basically the core, because every time it bounces off of it, the energy is so high. Every fraction of a second it bounces off so many electrons. Each time it loses some of its energy. Each time its wavelength gets longer and longer and longer, to the point that its wavelength becomes so long that it becomes visible. It becomes something like a blue or red or green or something that we can see, yellow. Combination of all of these colors, actually. Some of the X-rays, some of the ones that don't lose a lot of energy, they stay high. Some of them, they lose even more energy, they become infrared. But at the end, they make it out of the core, out of 100,000 years. Then it's a matter of seconds before they escape the sun. 300,000 kilometers per second, and it's 700,000. It's going to take about 2 seconds to escape the sun after that. The radiation zone, the convection zone, and then they come through the corona, the photosphere, and then the corona. Once they're out of the corona, they're actually basically coming through. Takes about 8 minutes for them to reach Earth. 150 million kilometers still, okay? So that's basically, which raises a very important point. I mean, in here, what happened if, let's say, for example, the sun gets more active right now and produces more photons? How do we know that? How do we know that this is happening in the sun? That's an important question that can be answered down the road in another unit about the processes inside the core of the sun. Anyway, during a solar eclipse, you can see more on the surface of the sun. You see this kind of hairy or prairie-like formations. These are actually a part of the chromosphere. In this case, these are the spicules. Okay, that's still kind of a part of the radiation. And then even above that, that's actually the sun atmosphere. So there is a corona, which has a super fast moving particles. Its temperature can be 1,000,000 Kelvin, but remember its density is a lot less. So the temperature is here about 5,800 Kelvin, but as you get higher and higher, the temperature is actually higher, but you can't feel it because it's super low. And it was measured by the Parker. Okay, again, the sun, its radiation can extend to some 90 astronomical units because of its solar activity, the magnetic field. And during during coronal mass ejection, those things, they can produce a lot of energy, a lot of fast-moving particles, mainly protons and electrons, okay? That can cause havoc, basically, on the solar system, including Earth, by the way. Thank you.